moving on to number 7. So what we're going to do here is see whether some interesting looking series converge. So there's a few different ways you might go about ones like these, but the goal here is I see 1 over n log n, and I think that looks like something I could integrate. So maybe I want to use the integral test here. So I need to check 1 over n log n is for sure positive and continuous, CTS. Also, 1 over n plus 1, log n plus 1. We know log and that no x are increasing functions. So this is going to be 1 over n log n. If I move to the next term, that's going to be smaller, because n plus 1 is bigger than n. So you divide by something bigger, you get something smaller. And the same story for log. All of this on 2 to infinity. So we can go ahead and do the integral test. So integral test, we can apply that because the function is positive, continuous, and decreasing. I look at the integral from 2 to infinity of 1 over n log n. And when I do this, I'm going to get u, let that be log of x. I'd rather these be x's than n's. There's nothing wrong with them being n's, but we have this. Okay. And then du would be 1 over x, u of 2 equals natural log of 2. And let's be very concise, limit or precise, limit as b goes to infinity of u of b is going to be infinity. So that says my new lower bound is log of 2. My upper bound is infinity, and I have 1 over u. So this is natural log of u, evaluated from log of 2 to infinity. So then we get the limit as b goes to infinity, just by definition, of the natural log of b minus the natural log of the natural log of 2, and I get infinity. So by the integral test, the series diverges, because the integral does. The series and integral must either converge or must both diverge. So the series diverges. Okay, how much room I have? A little bit more. So b, now we're looking at e to the n over e to the 2n minus 3. We have e to the n over e to the 2n minus 3. But I need to be careful because there's a sum. I think I started at 3 just to make extra sure it was defined there. Yeah, okay. So again, this function is definitely positive and is definitely continuous. We would worry about there being a discontinuity down there, but if I plug in 3, I get e to the 6. E to the 6 is definitely well past 3. In fact, even e squared is bigger than 3, so I could have started this at 1 if I wanted. This is positive and continuous, and if I look at the derivative, I get low e to the 2x minus 3 e to the n minus high d low, which is e to the x times e to the 2x divided by e to the 2n minus 3 squared. And so this I don't have to worry about, but let's see what happens. So these are going to cancel with these when you multiply. This looks kind of sloppy, but this is going to be e to the 2x squared when you multiply it out here. Same thing, when I multiply this, I'm going to get e to the 2x squared. So I'm left with minus 3 e to the x divided by e to the 2x minus 3 squared. And this is less than 0 for sure on 3 to infinity, because this is positive, this is the square of a number, so it's positive, and minus 3 is negative. So that lets me apply the integral test. So this one's a little bit of a doozy. So we integrate from 3 to infinity of e to the n over e to the 2n minus 3, except again I like these to be x's and not n's, because I like to think of n's as just natural numbers. So here I let u be e to the x, in which case du is also e to the x, and you might be thinking, okay, but then how is that helpful? Because this now becomes integral du over u squared minus 3. Because remember, e to the 2x is the same thing as e to the x squared. Okay, so I get du over u squared minus 3. Let's look at the new bounds. U of 3 is e cubed. The limit as b goes to infinity of u of b is also going to be infinity because I'm taking e to the b. So I get new bounds of e cubed in infinity, and I check that this converges. So how do I do this? I look at 1 over u squared minus 3. That's 1 over u minus root 3, u plus root 3. And I say that's equal to a over u minus root 3 plus b over u plus root 3. And now we figure out the coefficients. So 1 is equal to a times u plus root 3 plus b u minus root 3. And this is another one of those relatively easy partial fractions. If u is equal to minus root, let's plug in positive root 3 first actually. If u is equal to root 3, I get 1 equals 2 root 3a plus 0. So a is 1 over 2 root 3. And a similar argument can show you b is equal to minus 1 over 2 root 3 by plugging in u equals minus root 3. Okay. So now we actually have integral 1 over u minus root 3 minus u plus root 3, and then I have this 1 over 2 root 3. Because it was in both terms, I can just pull it out of the integral. Du. But now we have the magic of partial fractions. So this is 1 over 2 root 3 times the natural log u minus root 3 minus natural log u plus root 3 evaluated from e cubed to infinity. But we can actually write this. This is 1 over 2 root 3 natural log u minus root 3 over u plus root 3 evaluated from e cubed to infinity equals the limit as b goes to infinity, natural log of b minus root 3 over u b plus root 3 with a 1 over 2/3 out front, or 2 root 3. Minus natural log e cubed minus root 3 over e cubed plus root 3. We don't actually really care that much about this number. We're just interested in the limit because we need to see if this converges or not. But we see, what does this guy go to? That goes to 0. So I just get minus 1 over 2 root 3 because of the minus sign. Natural log e cubed minus root 3, e cubed plus root 3. And that looks really crazy, but it's just log of some number that's not 0. So the series converges by the integral test. Okay, so a little bit of work to do there, but we get what we want. The series converges. Okay. Also, this is 7b. Now we're going to look at 7c. And what do we get? Sum from k equals 0 to infinity of k times e to the minus k. So here I switched from n to k, but that doesn't change anything. And again, if I have k over e to the k, at this point you could actually use some other rules. So like, for example, ratio test would work to show this series converges. But let's go ahead and use integral test just to practice our integrals. Got that final coming up, right? Can't forget how to integrate. So first, k over e to the k is positive and increasing, or sorry, positive and continuous. So is it decreasing? The answer to that is not so easy. So we take a derivative. F prime of x is low d high, e to the k, minus high times the derivative of the low, k times e to the k, over e to the 2k. So now I factor out e to the k, and I have 1 minus k over e to the 2k, which is less than 0 if k is bigger than, greater than, or equal to 2. So I look and I see the sum is starting at 0, and maybe I'm scared because it's not decreasing everywhere, but it's decreasing on what we call a tail. So at some point you know that it's eventually decreasing, so we can say that this series is going to do the same thing as the integral. This is on 0 to infinity. So again, we can use the integral test. The integral test. Okay, so the integral from 0 to infinity, k e to the minus k, this looks like an integration by parts. So this is something a lot of people messed up on the last exam, was how to do integration by parts. So I get u, I want to be k, du is 1, that forces dv to be e to the minus k, but you get up here by integration, you get down here by derivatives. So this is going to be minus e to the minus k. You wouldn't have been in too much trouble if you accidentally took a derivative here, because that's the same. But don't expect that, know that for sure. Also, I was thinking this should be x, but since I'm changing it to u anyway, no reason to go back now. Actually, no, I'm not. This is going to be x, e to the minus x dx. Doesn't change anything, you can use k, but I like it to be x's. Minus x, e to the minus x, so I get uv. So this is minus x, e to the minus x, minus integral 0 to infinity of v du. So minus e to the minus x dx, evaluate this guy from 0 to infinity. So let's look at that. Limit as b goes to infinity of minus b e to the minus b minus 0 times e to the minus 0. That's just 0. Plus, because I have a minus and a minus, e to the minus x evaluated from 0 to infinity. And so we get, this is the same thing as limit b goes to infinity minus b over e to the b plus limit, I'm going to use a different letter, a goes to infinity of 1 over e to the a minus e to the minus 0, which is 1. So here, as b goes to infinity, what happens to this guy? This is a fact I gave you. So the b grows really fast, so this is 0. Same thing here, even better. You have an exponential, so this is 0. And then minus 1. And so you get that this thing converges. So the integral converges, which implies the series also converges. So you might think, okay, I could do this with the ratio test. Is there any advantage to the integral test? And the answer is, the big plus of doing the integral test is the integral test has a remainder theorem. So it tells you how much you could possibly be off by. So it gives you some idea of what the sum is. So that would be maybe one reason you might go out of your way to do the integral test versus the ratio. But that's problem number 7.